In continuation to the theory which I have given for calorimetry, here we are proceeding for some numericals. Hot water mixed with cold water is our concept. You have a calorimeter, okay, whose water equivalent, which means mass of calorimeter into specific heat of calorimeter is expressed as 10 gram, no issues. It contains 20 grams of water at 10 degrees centigrade. 15 grams of hot water at 80 degrees centigrade is poured into the calorimeter. Find the final temperature of the mixture after it attains equilibrium. For this purpose, I am assuming let some TE is the equilibrium temperature. Let us assume like that. Here, who are gainers and who are the losers? In fact, 15 grams hot water with the specific heat capacity 1 unit, of course, accordingly in CGS system. And it falls from a temperature of 80 to T. This is the loss part. Gain part is M calorimeter, S calorimeter, and it is at 10 degrees, don't forget. And temperature raised from 10 to T. Similarly, you have 20 grams of water. Same situation. So 15 times 80 minus TE is, this they have given as 10 units, 30 times TE minus 10. Now this is 2 times 80 minus TE is 2 TE minus 20. So finally 3 TE is 100. So finally 100 by 3, 33.33 degrees centigrade. Remember, that is the equilibrium temperature. And here, this is the gain part. So the technique which I've used here is the methods of mixer. This is the principle of calorimetry, right? Next, ice mixed to water. You have a calorimeter. Again, water equivalent is 10 grams. It contains 20 grams of water at 20 degrees centigrade. You have ice also. Ice at 0 degrees centigrade is added to the calorimeter. Okay, this we know. This also we know. Find the temperature of the mixture if the quantity of ice added is 4 grams. Again, gainers and losers. See, in the first part, you have a calorimeter, mass of calorimeter, specific heat of calorimeter, 10. For example, I am assuming this system is losing heat and finally falls to some 0 degrees. No, this is an estimation only. 20 into 1 into what are you going to know? Actually, this is 20. 20 minus 0. So it's a rough estimation, mind you. 30 into 20. This is 600 calories. Now see, you already know 80 calorie per gram is the latent heat of fusion of ice. For example, if 600 calories is the last, so that M ice into 80 is what I am doing. In fact, in this M ice is 60 by 8. So literally, that works around 60 by 8, right? That is around 7.5 grams. If you have 7.5 grams of ice, the possibility is equilibrium temperature might be 0 degrees centigrade. If it is more than that, there is a possibility that the entire mixture may fall down to sub-zero, below zero conditions. But under the first condition, you have 4 grams ice. 10 into 20 minus 0 plus 20. 1 minute. You cannot directly take 0 degrees. No? We have confirmed 7.5 grams is required for the equilibrium temperature to be at 0. So what I am assuming is maybe this 10 into 20 minus 0 calorimeter part, 20 minus some T, plus 20 into 20 minus T is 4 into 80 plus, now this is water, 4 into 1 into T minus 0. So this equation gives you what? This equation gives you the equilibrium temperature. So therefore, on proper working, you will have 200 minus 10T, 400 minus 20T, 320 plus 40. 600 minus 320, that will be 280, and this will be 3040. Right. So finally, what you want is 280 divided by 34. So the equilibrium temperature will work around some 8.23 degrees centigrade. Remember, this is the case where I am assuming 4 grams of ice as the given content. What if the quantity is 12? Undoubtedly, the total ice melts, and you may go to a sub-zero kind. No, 1 minute. Certain mass of ice is left. Only 7.5 grams of ice will melt. So certain gram of ice is left. Anytime in your mixture, if certain grams of ice is left, the equilibrium temperature of that mixture will be 0. Water and ice coexist implies equilibrium temperature is 0 degrees centigrade. So already I have done this workout. So therefore, in this case, what happens is 7.5 grams ice will melt. So which means some 4.5 gram ice is still left. So in the final mixture, you will have 4.5 gram ice plus 7.5 plus already you have 20 grams water. So basically 27.5 grams of water and calorimeter. All these at 0 degrees centigrade. That's the criteria. Okay. So in this problem, I have tried to explain you the estimation of equilibrium temperature. Remember, I have gone for a trial method. This is the trial method. Only then I have concluded what all my observations are. Next, industrial heating of water is a very famous situation. In a certain industrial process, what happens is 10 kg of water is to be heated from 20 degrees centigrade to 80 degrees centigrade per hour. Remember, this is per hour. For various practical reasons, it was decided to not heat the water directly. Steam at 150 degrees centigrade is passed from boiler into a copper coil immersed in the water. The steam condenses in the coil and returns to the boiler water at 90 degrees centigrade. What quantity of steam shall be passed per hour? Please remember, heat needed for heating 10 kg water from 20 degrees centigrade to 80 degrees centigrade. Let us calculate. So we'll calculate in calorie, which is very comfortable for us. 1 into 80 minus 20. This will be 6 into 10 power 5 calorie. This is required. So heat lost by 1 gram of steam in entire process. Can you please recall entire 150 degrees centigrade to 100 degrees centigrade? Change of state. And again 100 degrees centigrade to 90 degrees centigrade. 3 stages are involved. 1 into, I think, latent heat of, specific heat of water given, specific heat of steam, 0.8 into 50, because 150 to 100. Change of state, 1 into 540. 1 into 100 minus 90, 10. 8 5s are 40, 540, 10, 550 plus 40. This is a 590 calorie. Boys, you require 6 into 10 power 5 calorie per second calorie. See, let us now bring time into the picture. So in 1 hour, so what mass is required for you? Which is, you want this much and divided by 590, because per gram in an hour it is required. See, remember, this is heat required in 1 hour. This is heat lost per gram. So therefore that I am dividing this. With close monitoring, you will get a condition 1016 gram. So converted to kg, this is 1.017 kg. So you require, what is that? What is the question? What quantity of the steam shall be passed per hour? In fact, it is nearly 1 kg per hour. Okay? It's a very good question, actually. Good question. Measuring specific heat capacity in laboratory by methods of mixture. Actually, I have already taught you this, but I'll just brush up this a bit. See, basically, you are using this for a solid. I have a solid whose mass is m1, some lead short. I want the specific heat capacity of this solid to be measured. It is suspended inside a steam chamber to heat in, and a thermometer records its temperature as a T1 before I am dropping into the calorimeter. You have a copper calorimeter whose weight with the stirrer is M2. Sufficient quantity of water is poured, not more than 2/3, in the calorimeter so that the entire solid gets submerged in it. The calorimeter is weighed along with water to get the mass M3. Remember, M1 mass of solid alone, M2 empty calorimeter, M3 calorimeter plus water. And these things initially are at T2. Now you have dropped the solid, stirred well properly, so that some equilibrium temperature T0 is achieved. Right. Now, I am assuming specific heat of water to be S3, specific heat of copper calorimeter to be S2. That must be known to us, because you need to find only one unknown. You require a lot of knowns here. See, basically, what is happening here? Heat is lost by the solid, and heat is gained by the calorimeter plus water. This is the principle of calorimetry or methods of mixture. So, as you said, T0 is the equilibrium temperature. What am I going to do is, in this case, here you can see uh, heat lost M1 S1 T1 minus T0, heat gained calorimeter plus the water part. So you want S1. With this formula, you can use. So even you use the same method to measure the specific heat capacity of the liquid also. But for this purpose, you need to know S1. I am using the same equation actually. The same equation can be rewritten in this format also. Okay, right. A simple theory that you need to have some idea on this. Next. Till now, we are working with constant specific heat. And I am saying specific heat capacity of water, I am simply saying 1 calorie per gram per degree centigrade. What if some material specific heat changes with temperature? At very low temperature, the molar specific heat capacity of a rack varies some stone according to the relation C is equal to AT by T naught whole cube. Some data is given. Find the heat needed to raise the temperature of 80 grams of sample of the rock from 10 to 50 Kelvin. Before that, what about the number of moles in the sample? What is the difference between the specific heat capacity that I uttered in the previous questions and this question? In the previous question, it is gram. Now the one it is in mole. So therefore, the number of moles, you said 80 grams of the rock. 80 gram by they have given molecular mass of the rock 40. So you have 2 moles of quantity. Here, normally you will write delta Q as N C delta T. Normally, assuming C is constant. If C is not constant, you should write this as dt. Now do integration on both the sides. So this is delta Q, which is given by 2 times in the root A T cube by T naught cube dt. Here T 10 to 50 Kelvin. Fortunately, they are in Kelvins. So finally, this is 2 into 2000 into T naught cube is 300 to the power of 3 into 1 by 4 times 50 power 4 minus 10 power 4. Trust me, the entire thing will come down to 231.1 joule. Find the mean molar heat capacity. See, instantaneous and mean. What is a mean? Simple. You have now delta Q 231.1 which is in calories. And delta T, which is 40 Kelvin. The number of moles 2. So C average is nothing but delta Q by N delta T, which is 231.1 by 2 times 40. This will work around 2.88 joule per mole per Kelvin. Right. Remember, no confusion. This is at a temperature. This is average for the process. Right. The next question. What you have? A calorimeter of negligible heat capacity contains 400 grams of water at 5 degrees centigrade. 200 grams of water at 10 degrees centigrade. 400 grams ice at minus 60 degrees centigrade are added to the temperature. Find the final temperature of the contents of the calorimeter. My style is like this. Possible heat loss. Let us take possible heat loss, or else the most appreciable beggar in this is ice. See, 400 grams ice is what you have. 400 into specific heat of ice half. Minus 60 to 0, 60. Plus state change, 400 into 80. This is all in calories, remember. So this works around literally 44,000 calories. The best part from the beggar side. Now the losing part. 400 into 5 into, array, 1 already you know. Don't get confused. 1 into 5 plus 200 into 1 into 10 is. This is the losing side. So hardly that is 4,000 odd. Yeah, trust me. You can write this as 400 into 5, 400 into 5, 400 into 10, 4,000 calories. Fortunately, a calorimeter do not have any this part. So my understanding is that the beggar is dominating, whereas the donor do not have that much amount of funds. So what is going to happen? Now, ice point of view, again I am doing reverse calculations. 400 into half into 60, only for the change of state. Even that is also higher side, because 30 into 400, it is yeah, 12,000. So therefore, what we need to write is that, so it's a rough calculation. So what I need to write here is 400 grams ice at minus 60 degrees centigrade will come down to 0 degrees centigrade ice first. For this purpose, we require 400 into half into 60. This is 12,000 calorie. Hold on aside. Meanwhile, what is happening is the losing part. Already we have done the mixture, the total mixture will come down to 0 degrees centigrade by just losing only 4,000 calories. Thereafter, to meet balance 8,000 calorie, what would have happened is some part of water, I repeat, some part of water to meet here? 12,000 calories is freezing plus 4,000. So therefore, the freezing part gives another 8,000 calories. So M into 80 gives 8,000. The M is 100. Got the point now, 100 grams. So finally, what is happening is, I'll change the color. Finally, 400 grams ice minus 60 degrees to 0 degrees centigrade. Rest 400 grams plus 200 grams, 600 grams. That's what we have done calculation here. 400 and 200. 600 grams water, first converting to 0 degrees centigrade of ice, plus 100 grams water, freeze to ice. So finally, equilibrium temperature is 0 degrees centigrade. You have 500 grams of water and 500 grams of ice at that temperature. So therefore, finally, what is my conclusion? 500 grams ice, 500 grams of water. In this, what I have done, don't forget, this is a rough estimation, rough. So the beggar has a greater capacity, but the donor do not have that much capacity. So it is like your Dana Karna type. Next, 27. A copper tube of mass 200 gram slides down a rough inclined plane of inclination 37 degrees at a constant speed. The loss in mechanical energy goes into copper block as thermal energy. Find the increase in temperature of the block as it slides down through 60 centimeters. Remember, it has a slit by 60 centimeters. So therefore, when converted to height, it is 60 times sine 37, 3 by 5, 36 centimeters. You know how, right? So loss in potential energy is ms delta T. So therefore, M into 10 into 36 by 100 is M into 420 into temperature difference. So delta T finally is, here 1 minute, joule per kg Kelvin, right? ms delta T, right? Delta T is 36 by 100 times 42. There might be some error while I was working with this particular question, this particular book. I have done some changes in this that would have badly affected. Yes, trust me, that would have badly affected the digits. Right, no issues. Trust me, this is fact. It's a simple question. Right. So basically, what is to know in that is 36. This is 8.6 into 10 power minus 3. Minus 3 Kelvin. Right. Gas heater raises the temperature of 1 kg of water by 30 degrees in 10 minutes. How long will it take the same heater to raise the temperature of 3 kg of oil by same amount? At specific heat, Water is twice that of the oil. Simple. How long? The power delivered by the arrangement is fixed. All depends on ms delta T. Same heater to raise the temperature. Now, what are changing here? 3 kg oil, 1 kg water. Specific is also given. Power is a constant. So, T1 by T2 is M1 by M2 times S1 by S2. You said 10 minutes. T2 is also expressed in minutes. 1 kg, 3 kg. Specific heat of water is 2 times the specific heat of oil. So finally, T2 is 15 minutes. 15 minutes, basically. Next, 29. We have question number 29 to share. Right. So question number 29. Ball of mass 2.5 kg is heated to a temperature of 500 degrees centigrade and placed on a large ice block. When I said large means even some portion of ice melt, still ice is remaining. Means equilibrium temperature is 0 degrees centigrade. Assuming that heat is exchanged only between the ball and the ice, what is the maximum amount of the ice that can melt? Simple here, ms delta T is ml. That's all. So 2.5, here no issue. Specific heat 1 unit, temperature loss 500, mass, and this is 80. So finally, M is 2.5 into 500 by 80. Right. A specific heat of the ball 0.1 means 1 by 10. Right. 8,000. 800. 100 gone. 5, 2.5 is 12.5 by 8. So obviously 1.56. Because there is no other option available for us. 1.56 kg. Simple question. But while you are doing this, please note that this L and this L are made more or less calories part only. So there is no issue. 3 liquids with masses M1, M2, M3 are thoroughly mixed. And their initial temperature, they want, see, in this question, liquids are different, masses are different, their initial temperatures are different. I am assuming one among them is losing, the other are gaining. Let TE be the equilibrium temperature. So which means M1, S1, T1 minus TE is the last part. And I am assuming the gain part is M2, S2, TE minus T2 plus M3, S3, TE minus T3. So M1, S1, T1 plus M2, S2, T2 plus M3, S3, T3 divided by M1, S1 plus M2, S2 plus M3, S3 is equal to T equilibrium. This is the expression for equilibrium temperature. It's a famous relation also. Right. So you have uh, 10 grams of ice at 0 degrees centigrade. It is kept in a calorimeter of water equivalent to 10 grams. How much heat should be supplied to the system to convert the ice into vapor? Neglect the laws of heat to the surroundings and use the well-known values of specific heats and latent heat. First of all, 10 gram ice, 0 degree centigrade to 10 gram water at 0 degrees centigrade. So this requires 800 calorie. Good. Now 10 gram water 0 degrees centigrade to. Now don't forget, you have a calorimeter whose water equivalent is also 10 grams. And now onwards you count 20 grams from 0 degrees centigrade to 100 degrees centigrade. So this requires 2000 calorie. Done. And thereafter, water gets vaporized, which means 10 grams 100 degrees centigrade water to 10 grams steam. This is 5400 calorie. Remember now calorimeter remains at 100 degrees centigrade. So overall, what is the budget? 800, 2000, 5400, 7400 plus 800, 8200 calorie. That's the deal. Next. See, two solid objects of the same mass are supplied with heat at the same rate. The temperature of the first object with the latent heat of fusion L1 and specific heat capacity C1 changes according to the graph 1. Note that require a different color for this. So there, even though they took the same quantity of heat, slope is less for 2 when compared to 1. What is specific heat? It is nothing but delta Q by M times delta T. This is temperature difference. So obviously, if you take 2, that's very clear. Right. It is very clear from this. From this observation, it is very clear what is happening over there. Now you please comment on this part. See, very clear, slope is high, delta 2. So delta Q same. Same mass is also given. So very, yes, inversely proportional to delta T. Delta T2 less than delta T1. So in fact, C I should use, I think, C. So therefore, I should comment C1 less than C2. But whereas more heat is taken for state change in case of 2 when compared to 1. So therefore, L2 is greater than L1 because more time is taken in case of 2 when compared to 1. Compared to 1. Next. The next question. A direct question. Water is boiling in a large vessel as shown in figure. Another smaller vessel contains water is dipped in the bigger vessel as shown. The vessel is open at the top. Water in smaller vessel. See, it cannot boil. Why? Because suppose if it reaches 100 degrees centigrade, maximum this liquid reaches 100 degrees centigrade, and thereafter no transfer of energy takes place from the outside to inside part because they attain same temperature. So you cannot boil. Right. Next, 35th question. What you have is See, in this particular case, what we have is ice at 0 degrees centigrade is added to 200 grams of water initially at 70 degrees centigrade in a vacuum flask. When 50 grams of ice, you can see that very clearly here, 50 grams of ice is added. What is happening? All ice has melted the and has all melted. The temperature of the flask and contains is 40. Stay here for a while. 50 grams of ice has been added and has all melted. The temperature of the flask and contains 40. Hold on. What is happening is 50 into 80 plus 50 into 1 into 40 minus 0. All this is gain part. So now this is equivalent to loss part. 200 grams of water initially at what is that? 200 grams of water at 70. Actually, I have used 80. Frankly speaking, I should not use 80. I should not use 80. I need to find that only. L. And right. Right. Oh, right. 50L plus 2000 is 14,000. So 50L is, see, may I assume, I think 50 grams at 0 degrees centigrade melts and then heated up to 40, right? That part I have written. 50 into 40, right? Heat lost by water as it cools from 70 to 40. Kada. This is 70 to 40. So I should be careful in such calculation. It says 6,000. So which allows 50L. And one more important point is you have water equivalent. That should be mentioned. You have what do you call the calorie meter content also you should consider. No, because flask is also there. C into 70 minus 40. This is 30 times C, equation 1. So two unknowns, right? When a further 80 grams of oil has been added and has all melted, the temperature of the whole is 10 degrees centigrade, which means 80L plus 80 times 1 into 10. This is the gain part. Now, what is the loss part? The last part is you have 50 grams of water at 40 degrees centigrade plus 200 grams of water at 40 degrees centigrade. So 250 into 1 into 40 minus 10 plus, don't forget, calorimeter is also at 40 degrees centigrade, falling down to 10, which is again 30C. Equation 2. Boys, now equation 2 minus equation 1 you take. Now, by doing which, you will get 30L plus 800 minus 2000. You will get maybe minus 1200 here. What about here? 30C gets cancelled. 250 into 30. That is 7,500. 7,500 minus 6,000. So 30L is 1200 plus 1500. 2700. Implies L is 90 calorie per gram. Just see anywhere did I went wrong. 1 minute. I think I can 250 into for a year 1000. This is 1000. 40 minus 10 is right. 30 7,500. Just do that calculation once again carefully. Right. 36. The specific heat of a metal at low temperature varies according to the relation AT cube, where A is a constant, T is the absolute temperature. The heat energy needed to raise the temperature of unit mass of the metal from 1 Kelvin to 2 Kelvin. Just now we have done this question. Delta Q is unit mass 1 into S into dt. This is nothing but AT cube dt 1 to 2. So this is A by 4 times 2 power 4 minus 1. Power 4 is 16, 15A by 4. Easy question, basically. 37th question. The graph shown in the figure represents the change in temperature of 5 kg of a substance as is observed heat at a constant rate, 42 kilojoule per minute. The latent heat of vaporization of the substances. See, this is the melting and this is the vaporization. So you need to worry only this part. That is 10 minutes. 10 minutes into 42 kilo. Remember, this much heat is taken for the melting purpose of 5 kg of the substance. So L finally is 84 into 10 to the power of 3 joule per kg, or 84 kilojoule per kg. Easy. Just focus on this part. Right. Because remember, this part is latent heat of vaporization, latent heat of fusion. Right. Next thing. In a container of negligible heat capacity, what you have is 200 grams ice at 0 degrees centigrade. 100 grams of steam are added to 200 grams of water that has temperature 55. Assume no heat loss to the surroundings, and the pressure in the container is constant. Negligible heat capacity is a very good news for me, actually. Negligible heat capacity is very good news for me. Right. See, first, let us work like this. 200 grams ice It's a journey to 200 grams of ice at 0 degrees centigrade to 200 gram of water at 0 degrees centigrade, 200 grams of water at 100 degrees centigrade. Boss, totally this will become 200 times 80 plus 100. That works around 180 into 200. 36 kilos of kilocalories actually. Let me kilocalorie. Hold. There is water also you have. 200 grams of water at 55 degrees centigrade. 200 grams of water at 55 degrees centigrade to 100 degrees centigrade is again 200 into 200 into 45. 9,000. 9 kilocalorie. So overall 36 plus 9, 45 kilocalorie is required. Now you have steam, how much? 1 gram, 100 grams of steam. See, what we need to do is 45 into 10 power 3 divided by 540, because 540 is by doing which 83.33. Remember, this much amount of steam will condense. Means some steam is left. Steam is left. Plus water at 100 degrees centigrade coexists. This results equilibrium temperature is 100 degrees centigrade. A is correct. Final mass of water, obviously, you have 200 plus 200 plus 83.33, right? So this is wrong. This is wrong. Right. 14th question in this. See, in this part, lead bullet just melts when it hits an obstacle and stops. Assume that 25% of the energy dissipated is absorbed by the obstacle. Find the speed of the bullet if the initial temperature is 27, melting point 327. See, mass into specific heat into delta T. Once it reaches here, plus ml. These are the required heat for melting, and 3/4 of half mv square. Find the speed of the bullet required. So that's all. Just solve this from here. Use the given data properly. You will get V as 410 meter per second. Very high. Remember, change of temperature, state change, both. 15th question. Earthen pitcher loses 1 gram, or our pot, Indian pot. 1 gram water per minute due to evaporation. Water equivalent of the pitcher is 0.5 kg. Pitcher contains 19.5 kg water. Assume that the heat loss is mainly due to evaporation for the given temperature range. The specific latent heat of vaporization of water is 580. Water also, vaporization of water given, area L given, S given. Right. No issues. So what is happening here? So due to the evaporation, it draws heat from the water inside. Let us see after some time, T, mass of water is minus, you said 1 gram per minute. So because I have converted into kgs, grams, sorry, that's gram. So at this T, temperature is a T. And at that instant, change in temperature is a delta T, which means T to T plus dt interval, which means 19,500 minus T S dt is evaporation rate 1 gram per minute, which means this is mass of water evaporated per minute, evaporated in dt time. So which means latent heat of fusion of ice, that's given. So clearly integral dt by LF by S. Here, don't forget, initial temperature is a 30. You want the temperature after some time. The two after an hour, 60. So this is 30 minus T is LF 580 S 10 power 3. Kilocalorie per kg, that you can compensate with 1 minus 1 because of integration. Log E 19,500 minus T by 19,500. Just solve this. They are given everything required. And 19,500 minus T means 60 here. So T is 30 minus 580 into natural logarithm of 1950 by 1944. Solving, you will get 28.21 degrees centigrade. So hardly 1.8 degrees centigrade have fallen down because of keeping water in this. Right. I'll just stop over here. The second part, I will release it on the other day.